Hi everyone, I am Aditya and I am a software engineer at Salesforce. Today I am going to talk about how we automated third-party dependency management in Bazel Monorepos. I am going to start with some background. So our team manages 3 language-specific monorepos, Java, Golang and Python. We have over 500 projects built across them, and each of the monorepo has its own set of third-party dependencies. That is jars in Java, modules in Golang and packages in Python. We have over 95% of the projects following the single version policy with a few exceptions. Before talking about how we automated the third-party dependency management, let's see why dependency automation matters. Manual upgrades are slow, inconsistent, and they don't scale well. Upgrading single dependencies manually can often lead to hidden incompatibilities over time. Non-vulnerable dependencies are often never prioritized as compared to vulnerable dependencies. And dependency automation brings reliability, repeatability, and safety. So our goal is to keep dependency graphs clean, secure, and aligned, minimize developer involvement in routine updates, and make upgrades effortless, safe, and traceable. Let's see how we did this. So we have built a system, and there are 6 different steps involved, starting with the detection of upgrade opportunities, which is basically the number of dependencies for which an upgrade is available. So once we have detected the upgrade opportunities, the next step is to rank these opportunities by impact, and there are several factors using which we do that, including the type of dependency upgrade, usage of the dependency, version lag, and security. So once we have the ranked opportunities, the next step is to propose changes, and the outcome of this step is the system proposes one or more than one dependencies to be upgraded. I will be talking about these steps in more details in the next slides, but for now, let's say the system has proposed one or more than one dependencies. The next step is that we send a pull request and filter the impacted targets by using bazel-diff. This is to make sure that we are not building the whole monorepo and instead just focusing on the targets which are really impacted from the upgrade. So once we have the list of these impacted targets, the next step is to validate them by using Bazel build and Bazel test. And if the validation is successful, the next step is to publish these updated artifacts to the registry. So these new artifacts will contain the new version of the dependencies, and this is how all our project owners got the upgrades for free. Let's deep dive a little bit now into the algorithm that we use. So the first step is to basically rank the upgrade, and we do follow some priority orders, starting with we prefer vulnerable dependency upgrades over non-vulnerable dependency upgrades. I know I just said that non-vulnerable dependencies are not prioritized, but with dependency automation, we make sure that they do. And the next order is usage of the dependency. So we prefer a dependency with low usage over a dependency with high usage. And the reason is that the number of impacted targets for a dependency with low usage will be less as compared to the one with high usage. And as a result, the probability of that dependency with low usage of getting merged will be more. The next one is the type of the dependency upgrade, which is basically we prefer patch upgrades over minor upgrades and minor upgrades over major upgrades. So once we have a list of these ranked opportunities, the next step is to pick a random candidate from these top upgrades. So on the screen, you can see that there is an image and there are 100 dependencies ranked from 1 to 100. In this list, the dependency ranked as 1 is the most favorable one to be upgraded. So earlier back in the days, we always used to pick the dependency which is ranked as 1. But soon we realized that it's not an optimal approach, because let's say if this dependency upgrade is a bad upgrade, in that case what's going to happen is automation will stuck on the bad upgrade, and someone has to manually intervene to unblock it. And definition of a bad upgrade is that an upgrade for which there is a build or a test failure. So to improvise the approach, we now pick a random candidate instead of picking the dependency with rank 1. So in the same example, we are picking a random candidate from the top 10 upgrades, and let's say we have picked 2. The next step is we check that if this candidate is present in our ignore list or not. So we do maintain a global ignore list, and the purpose is that we want the dependency automation to ignore all the dependencies present in this list. And there are several reasons to maintain this list, including dependencies for which a toolchain upgrade is required, or we have some dependencies for which there are licensing issues, and we prefer to upgrade these kind of dependencies manually. Okay, so once we verify that the picked candidate is not in the list, not in the ignored list, the next step is to club dependency upgrades from the same groups. So in the same example, there are 2 more dependency upgrades ranked as 10 and 20. So if you'll see, they belong to the same group G as were the original picked dependency, which was ranked as 2. And target version of all of these dependency upgrades is also same. So as a result, all of these dependency upgrades are clubbed together, and system suggests, okay, let's upgrade 2, 10, and 20 together instead of just upgrading 2. So finally, upgrade is sent and validated. Just a quick recap now. So the automation runs periodically as part of our CI pipeline, and it uses bazel-diff to limit builds and tests to impacted targets. And these targets are then validated, and we make sure that there is no build or test failure. And this is how we have integrated the automation into our Bazel workflow. Yeah, cool. So now let's see a quick example. On the left side of screen, there are 3 dependencies, A, B, and C, where A and B, they belong to the same group, and dependency C is from a different group. And in the center, there are 3 images. Image 1 is using dependency A, image 2 is using dependency B, and image 3 is using both dependencies B and C. So now let's see what happens if automation picks, like these 3 images. So let's say if automation has picked dependency A or dependency B to be upgraded. In that case, what happens is, given that they are from the same group and the target version of their upgrades is also same, they will be eventually clubbed into the same group, and as a result, they will be upgraded together. So it won't matter if dependency automation is picking A or B to be upgraded, because they will be upgraded together. And okay, so you see, like all of the images are impacted from these dependencies, and they will be published. But let's say now instead of A and B, if dependency automation picks dependency C to be upgraded, in that case there is only one impacted image which will be published, that is image 3. Yeah. Let's see some results now. So the dependency automation has upgraded over 1,500 dependencies in the last 18 months and saved more than 2,000 dev hours, which is great. No automation is perfect, neither is ours. There are some challenges that we are facing, starting with occasional upgrade slowdowns, which is basically even after picking upgrades randomly, there is still a chance that most of them are bad upgrades, due to which there will be a slowdown, and we have to manually intervene and unblock the automation. The second challenge is that the automation doesn't know when to give up or retry. So I will explain this by using a very simple example. So let's say there is a pull request to upgrade some dependencies, and there is a build failure. So there can be several reasons for that failure, right? So most common error is that most of you have seen as well is a test failure. So in that case, ideally automation should just give up on that upgrade. And the other reason is that, let's say there is a CI flakiness due to which the build has failed. In that case, automation should ideally retry. But automation doesn't have access to logs, due to which it can't. And honestly, we haven't added AI in this automation, due to which, even if it has access to the logs, it can't say that if it has to give up or retry. And this is another challenge to solve. So there are some existing solutions which can help, but they have their own challenges, and we can't entirely rely on them. We have used some of these existing solutions before, but they don't really work well with Bazel. I mean, they are pretty good for repositories with small number of dependencies, but our monorepos are pretty big. Just talking about the Java monorepo we have, it has over 1,700 dependencies in it. But I'm not saying that these solutions are bad or something. It's like, in fact, we are using some of these solutions to upgrade the Docker images in our monorepos, but we entirely rely on our own custom solution to upgrade third-party dependencies. So what we want as a next step is to club these enterprise solutions, and so that we can have benefits from all the ecosystems. I think that's all. Thank you for listening. And just to mention, so we have some open source projects from our team. So if you're interested, please check them out. Thank you.